afternoon, class. In today's video, what I'd like to do is to talk about the electric field. So to think about the electric field, what you have to do is we'll start with a picture of it, and then I'll go into all of the equations that go along with the electric field. So to start with, we have protons and electrons are two fundamental elementary particles when it comes to electric charge. Okay? A proton would be given by this diagram with a positive charge and the electron with the negative charge. Okay? Now, the way that we define what a proton and electron are in terms of how their electric fields are drawn is that traditionally you would draw the electric field, which by the way extends to infinity. So it goes in all directions all the way across the universe. So wherever there's a proton or an electron, you have a charge, and that electric field is coming out of is being emitted from that charge. Okay? Now, so whichever way that the field is facing, or is pointing whatever direction the field is pointing in, you can tell what kind of charge it is. Now, I do want to caution you on this in terms of fundamental concepts, like the concept that you have in your head on this one. You can't think of these field lines as forces. Like, I know we've described forces with lines like this as well. These are not forces. So it's not like this is a proton and it is pushing outward or something like that, or this is an electron, so everything is collapsing in on it. That's actually not what's going on. It's just to show you what direction the field is pointing. And that will determine how it interacts. They actually interact in the exact same manner when it comes to how opposite charges interact with each other, and how opposite charges interact, and how similar charges interact. So I just want to make sure that that's very clear. So in this case, because I've got a proton and an electron right next to each other, their fields will interact, obviously. But how do they interact? Well, the thing is, that's why we point I take the time to draw out all the different field lines, and I show which way they point, because with the electron, the traditional method is to draw the field lines coming in towards the electron. That has nothing to do with any physics or any fundamental concepts. That's just the traditional way of drawing the field lines, and it's worked as a norm for scientists. So if you ever feel like that the direction of it needs to be changed or needs to be different, just know that that's not something that is, it's debatable. You can feel free to change the direction as you feel comfortable. However, just know that this is the traditional way of doing it. So if you read a textbook, you will see that the field lines will be drawn this way, and that's how almost every physicist and engineer will draw these field lines and understand and visualize the field lines in their head. So just to keep that in mind. But just like gravity, if you wanted up to be positive or down to be positive, that was totally up to you. So, if you wanted to flip the way that these signs are, or the way the field lines point, that's totally fine, as long as you're consistent and as long as you mark that down somewhere. Like if you write over here that positive points in and negative points out, that's fine. Having said that, so as you can see, what the field lines tend to do is they don't actually oppose each other. They actually just, what's going on is they're starting to bend and interact with each other. So as you can see, the charges, because they're opposite, you get that rule that you learned in elementary school where opposites attract. Opposite charges attract and like charges repel. And that's actually true. And you can see this because the field lines point in the same direction. So the positive proton has its field lines pointing out, and the negative electron has the field lines pointing in, or at least in the opposite direction. So therefore, the field lines flow this way. This would keep the two charges close to each other. They would keep the charges close to each other because there is an electrical attraction between the two. That's actually quite powerful. It's about 100 times stronger than gravity. So that's why if you've ever seen electric forces or if you've ever seen like in cartoons when somebody gets shocked and they go flying through the air, that's actually a real effect, because you can, if you put enough of an electric field, you can actually float things, because electricity is fundamentally stronger than gravity. So, having gone through some of that conceptual basis, let's go into the actual equation for electricity, or the electric field, which is E equals kq over r squared. Hopefully that starts to look a little bit familiar, especially when we talk about when we did universal gravitation. And in fact, this should look a little familiar too, because those field lines look kind of like gravitational field lines, and you would be correct. It's just that some of them either point out and some of them point in, whereas with gravity, they only pointed in. So the difference here is, that's the main difference between electric fields and gravitational fields. So again, let's make sure that that is cleared up and keep that in mind. What I've also introduced here is this another fundamental constant, which is K. That is the electrical constant. And so that would be 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Again, hopefully that looks familiar, given that the universal gravitational constant was Newton meter squared per kilogram squared. So, given that, let's also take note. This Q could be any charge. Okay, this because this is a variable right here. You don't have to think, oh, it has to be an electron. It has to be an electron's charge or something like that. It could be 1 coulomb. It could be 1,000 coulombs. It could be a millicoulomb. It doesn't matter. However, if we're talking about the electron, which is why I wanted to introduce it to you guys in this video, because you will be, it's just one of those fundamental constants that we've measured in nature, and that it's worth going over. So the fundamental charge for any particle is 1.602 times 10 to the negative 19th coulombs. For an electron, this is negative. For a proton, this is positive. So I want to make sure that that's very clear. Said that very slowly so that you can see me say that again over and over throughout this as you replay this video as you need to. The other thing I wanted to point out was that r is the distance between charges. This is in meters. Normally, or at least with gravity, we would have written this with d or maybe h for distance or height. The reason why I didn't want to do that for this one is because these charges are so small that the how small the charges are compared to gravitational forces and things that we have seen in our everyday life that would give us an idea of what height and distance are. These are so close together that doesn't really have any real world analogy to it. So I didn't want you to think, oh, this is just distance. So that's why I made it a different variable. This is, by the way, the more traditional variable that would be written in higher level textbooks and all of that. So I don't want you to think, oh, but it should be D, right? No, it can be D, it could be H, it could be R. R is just the more technical one because it's a little bit more general. So if you're looking at it from a more general perspective, R would be the better variable, but it's always measured in meters. So ultimately, it's not that important. It's just I want to make sure that all of those things are said, so that when you see higher level textbooks that maybe write it with different variables, you will see that this is it is something that you need to keep in mind, that it is just the way physicists have generally written out all of the formulas, and they don't have any fundamental difference in their meanings. So now the last one that I wanted to go over was this concept of lightning. And this is one of those things where it is very difficult to understand, because lightning, unlike what you may have been shown in movies and TV, is not a phenomenon that occurs. So, like what you may have seen in movies is that people can dodge lightning. Maybe you've seen that in some video games as well, like Final Fantasy X for you gamers out there. Lightning, however, you have to understand, as it is a phenomenon in nature, it does need to be explained and it needs to be understood, but it is not a thing that happens. Because if it was a thing that happened, you actually could dodge lightning. It might be possible if that was the case. However, lightning is, you have to think of it more of as a condition that is met. Once the condition is met, lightning occurs. And the condition is when the electric field is 1 times 10 to the 6 newtons per coulomb. So when it's 1,000,000 newtons per coulomb, lightning will strike. However that occurs. It could be that the charge is big enough. It could be that the distance is small enough that gets that electric field to that magic number, and then boom, lightning occurs. Okay, I want you to keep that in mind, because a lot of times what we do is we think of because we think of lightning as a thing that occurs. So I want to make sure I emphasize that it is a condition that is met. If that condition is not met, lightning doesn't strike. So, and the one I usually like to do is when it comes to being legally married. Okay, you can say whatever you want, but until you legally sign the legal documents that say you are husband and wife, in the eyes of the law, you're not married. So, I could have in terms of, and again, before we talk about any religious things, I'm just talking about legally here in America. Until you sign that marriage certificate, you're not married. It's a condition that must be met. You must have signed it to be married in terms of that, in terms of that status being granted to you under the eyes of the law. In the same way, when it comes to lightning, if the conditions are not right, if the distance is too far, if the charge is not high enough, lightning will not strike, ever. So you can't dodge lightning, because it just means that if you try to dodge the lightning, that just means that you change the conditions enough where lightning wouldn't strike you, it struck something else. So that's why they always say, don't take like something, this is made out of wood, but maybe this metal tip of it, don't bring it closer to the clouds, because the higher up you hold it, the closer it's to the cloud, and the less the distance is, which could attract the lightning. Now, like I said, attraction, that's not really a thing. You're not really attracting the lightning. What you're doing is you are making the conditions more favorable to having lightning strike. So I just wanted to make sure that was hopefully a little bit clearer. Now, of course, if you have any other questions, please let me know and I can do a follow-up video to this. But that concludes how to think about electric fields. Good luck in your studies, and may the force be with you.